welcome everyone. Thanks for coming to the session. My name is Matt Kosovec. I'm a data engineer by trade, been doing it for about 10 years. Lots of different technologies over the years. Started out with good old SSIS back in the day, then spent a number of the years in the Hadoop stack, Spark, spent some time on distributed computing systems, Mongo, Cassandra, DataStax, all these companies that are still around but are doing completely different things when I did it. About 6 years ago, my partner and I spent a bunch of time and effort thinking about how to rework and rethink how you build your data code in order to make it more extensible. Basically, everyone's been through the problem. We'll walk through it today, but that's what we're going to be reviewing today. Is basically what are the main problems with building extensible data code? We're going to walk through kind of step 1, 2, 3. A number of different principles that we're going to try to apply from software engineering and talk through what those principles are, what they mean, why they're hard to do in data engineering. And then, of course, we're going to talk a little bit about data forge at the end of it, but primarily about how we apply those software engineering concepts to the data space, and then what we've done and how we solve for it. So again, thanks so much for coming, and that's it. I guess a little bit else about me. I'm from Chicago. I got 2 cats. I got a wife. She's awesome. I'm ready to take a nap when I get home today, so been fun times. And just for, again, everyone else, DataForge, we're a carve-out from a big corporate consulting firm. So if you haven't heard of us, we're only about 6 months old, but the product was in development for about 6 years. So if you guys, we're going to go over just the basics today of what's the core piece of it and why it's interesting. But there's a lot of stuff to come hang out with us and learn about upstairs. And of course, we got all the fun demos and stuff. Okay. So I think if you guys are all data engineers in this room, you've seen this story before. It's the classic, here's my requirements. We got 3 tables, we got maybe a dimensional model we're going to push to on the other side, we got our kind of landing zone, we got a couple of transformation layers in the middle there, and then we're going to basically publish out. So not too bad, pretty straightforward, easy to work with. Okay, all of a sudden there's actually a CSV file that we didn't think about. That is coming in off the side. All right, now we gotta build another flow, do a couple back and forths, do a little loop to flip to throw it back into the other piece of the code we already built. Still not so bad, pretty doable. Now we have a new source system. How do we plug that in, right? We got a bunch more tables we need to pull from, maybe a different database, a couple more files, and all of a sudden it's all right, well, we already built this nice thing up here. I don't want to throw it all away, so let's just add some stuff down here and let's make it interoperate and let's find a way to then plug it in and make it all work, right? So this is traditional pipeline development, right? And the question always then becomes is how much of what you already built do you rip up in order to then replace and make it more elegant and more beautiful and easier to maintain, all that stuff. And so this is still not so bad though, right? You can deal with this. The problem is 2-3 years later, it's chaos. So this is a real customer environment, about 5-6 years of development, a couple hundred, close to 1,000 tables that we're working on the intermediary steps, many stored procedures, many SQL views, and a lot of pipelines. And so, you end up starting somewhere, thinking everything's going well, you tack on, and you make art. And my favorite piece of this is this like black hole or colorful hole of death. This is just a whole bunch of random code artifacts that did nothing, that were just out there, that were like old stuff that the data set either disappeared, it wasn't used anymore, the target disappeared, it wasn't used anymore. But they're like, well, we don't want to touch anything because we don't know what it does. And so let's just not touch it. And so there you go. And you got all these it's art, right?
Looks like it's protecting the stuff to the right.
Yeah. It's like a little shield right after the ball.
Yeah, so again, this is, I think, if you guys have been in the industry, you've seen this before. So this is what we saw. This is actually, again, 6 years ago, the customer we were working with that really launched us into this whole journey to start thinking about how to apply software engineering best practices and take some ideas and start applying them to the data space to try to prevent this disaster. So today we're going to be going through 3 different software engineering principles. If you've, again, worked in software engineering, these shouldn't be if you didn't know the names of them, once we walk through the concepts, you'll be like, oh yeah, that thing, I understand. But they all have nice, kind of catchy names. So we're going to be using their catchy names because they're fun to talk about. We got dry, don't repeat yourself, single responsibility principle, which is also known as separation of concerns. And then finally, pure functions only. This is kind of our goal. This is where we want to be. Functional programming is becoming very popular for good reason, especially in the software space. And that's ultimately what we're going to drive towards, is how can we make data engineering programming, data engineering development more functional, even when there's some limitations and some challenges along the way. Okay, first, we start with dry. This is my favorite because the puns are fantastic. So again, most important, don't be wet. What does wet stand for? Write everything twice. So again, oftentimes, right, especially in SQL, we got this statement and this statement. We're going to go through an example. Oftentimes, there's a lot of code overlap, right? So getting away from this is basically trying to reduce code duplication. The rule of 3 in software engineering is if you've copy pasted it once, okay, you can get away with it, fine. We've all been there. But if you're copy pasting twice and you have 3 copies of it, that's the time you're going to move it to a class. You're going to move it to a separate function, right? You want to get it out of the copy paste mode and you want to get it into its own separate singularity or whatever you want to call it, to then reference, right? In those 3 locations that you actually need to use that logic. This one's my favorite because it fits what I've been spending my life on for the last 5 years really well, which is every piece of knowledge being code, logic, state, data elements, whatever you want to call it, should have a single, unambiguous, and authoritative representation in the system, right? We all have these things in our head we're trying to put into code in order to do something with that data, or with that transformation. Every little bit of that code, every little sub-bit of that knowledge, everything we need to do should only have one place to live. It's got multiple places to live or multiple potential places to live. It ends up being way more difficult to manage, way more difficult to then extend, and most importantly, you're often just constantly refactoring, right, in order to get everything into a better place. So ways today, without all the cool stuff we're going to be talking about later, to dry off, is CTEs, right? Hey, I'm going to write some a with statement at the top of my SQL, and then I'm going to reuse that result of that with statement 4 or 5 times, right, later on down in my SQL. That's a great way to prevent code reuse, right? You're not writing the same logic over and over, so on and so forth. Views, materialized tables, right? These are, of course, what we kind of saw before, right? Hey, let's persist the data. Basically take my result set and put it somewhere so that it can then be referenced by many things downstream. Of course, that can be with both views and you can actually store the data depending on performance and a million reasons to do one or the other. Macros, UDFs. Macros are kind of a DBT concept, but essentially, right, what is a code snippet that I can then parameterize? I got variables, right, that I maybe want to inject depending on where that code is being used. Those are very common ways to, again, prevent code reuse. You at least are, taking kind of a template, right, and then you're just plugging in the variables there. So at the very least, the template's not reusable and you're managing that in one place. Or, classically, a package, right? Hey, let's put all this stuff into a black box, treat it like a black box, and then I can copy paste that black box in many different places. This one's probably the least applicable because in the data engineering space, oftentimes that package is tied to a schema, right? And so you necessarily need to have the same input columns and the same output columns with the same names and data types in order for that all to work the same way, which is super rare, but sometimes it's out there. Primary challenges. If we have time at the end, depending how quickly I talk, we're maybe revisit encapsulation and composability, some advanced concepts, dependency management, refactoring, regression testing. I've touched on some of these. Dependency management is a big one. It'll come through in our example we go through in a second. And encapsulation and composability, that will come through when we get into some of the later concepts, but I'll just briefly touch on it that your kind of smallest unit of work in the data engineering space by default is one SQL statement, right? Select all the way through the from statement, right? Or maybe whatever, you got your havings and other things after that, but that's typically your unit of work, right? Very often it's hard to break it down from there further because you're not really putting it all, right? We work in sets, right? We don't really work in functions, we work in set-based logic of this data set, and this data set, and this data set come together, and then we publish a new data set. So the fact that the lowest, smallest unit of work is essentially a data set or a table or a SQL statement ultimately ends up being a challenge. And we'll talk about it later, but again, that's kind of the very high level of what encapsulation. And then finally, really quick, composability. How easy is it for you to take your small snippets of code and reuse them in many different places, right? Not just in like specific places, but basically how generic is your small snippet to then be reused in many different places. Composability, right? When you're composing something, you're taking a bunch of small things and you're putting it together versus building specific small things and then putting them together, if that makes sense. Like I said, we'll revisit it, but wanted to give you guys a brief overview before we dig in. All right, enough theory. Let's talk a real example. This is a pretty classic wet versus dry, example. Left-hand side, we got the BI use case. Let's just say it's a denormalized table. I want to plug it into Power BI, and I want to do some drag and drop reporting, rather than my end users having to understand the data model and a bunch of joins and things. I'm going to just pre-join it, and I'm just going to give them a flat data set. They can plug it in, do some drag and drop, all good. No aggregations. They want the transactional level. Power BI will aggregate it for me, right, as they kind of drag and drop their stuff. So that's left side. Right-hand side, data science use case. We got feature engineering. Data science models, oftentimes when you're training them, the data that's going into them needs to be at a very specific grain, with very specific aggregations, with very specific elements for the individual features and the dimensions that are along with it. So this is really coming from the exact same, if you look closely, which you probably can't because it's way too small, but these are the exact same tables that are in both of these sites. And everything highlighted is actually the exact same code. You got two completely different data sets that you're publishing to. You got two completely different targets in terms of the resulting grain of data, the resulting elements of that data. However, there's so much code overlap. So how do we solve this? Today, you create an extra layer. And so this is again, we talked about CTEs, or we talked about persistent tables. The most common way is said, well, hey, I'm a smart data engineer. I know that I can basically derive the feature table from the BI table. So I'm going to first build my BI table, first layer here, and then I'm going to store it, and then I'm going to take the resulting data set, and I'm going to build my feature table, because now I've eliminated all of that code duplication, and I'm able to make it much more concise, a much smaller statement here, way less yellow code. Yellow code is bad code. And now I've isolated the kind of two layers of logic into two different use cases. So this is great, right? We now have less code duplication. We've only put the logic in one place, so that if I need to make changes, it's one place to go to. I don't need to make it in both places if I have a change in requirements. However, there's downsides, significant downsides. Specifically, if you change something on the BI side, because hey, the report needs to look a little bit different, you could accidentally completely break the feature side, right? You now have this logical dependency chain that is encapsulated in the table itself versus the one piece of code or etc. And then of course, you've created an extra layer of orchestration, which then means it's slower to refresh. You're not doing these things in parallel anymore. You have to chain them together, right? First, I need to run the BI. It needs to write to the table, finish that, then I go to the next step, and then it goes on from there. So this example is relatively simple, because this is a relatively short talk. But as you can imagine, going back to our initial slides, do this over, and over, and you end up with really long chains and a whole bunch of extra steps just to try to clean up your code. And this is if you get the opportunity to refactor, which you don't always get the opportunity to do. Finally, you can't always do it, right? Sometimes just based off of the logic, the business requirements, the cadences, whatever it may be, you can't necessarily make your code super dry because you end up struggling to find a way to take one data set and turn it into something that is more or less repeated code. Questions, feedback, ideas so far? Again, we're just going through each one of these three principles and then saying, hey, this is the goal, this is why it's hard, and then we're going to talk about the cool stuff about how we solve these problems. Good so far? Great. Next up, single responsibility principle. Separation of concerns. This is, as an architect, this is one of my favorites. Saves your butt so many ways. So the language here is a little ambiguous, kind of by definition, but super powerful. It takes a little while to think about it, right? You want to gather together the things that change for the same reasons. It's not about things that are necessarily similar. It's how do things from outside the world want to change the things that are similar. So instead of thinking about like, this looks similar to this, you think about what are the ways that things change and how do I then group those things together? And then identically, you want to separate the things that change for different reasons. So I'll just say this is a good one to kind of do some homework on, see some more examples, especially if you see it in the software engineering space, it starts to kind of click a little bit better. But I like to put it in more plain English, right? Anything everywhere, wherever you like, which is how pipelines are. Hey, you can do your change data capture as like the last step of the process, or you can do it at the beginning, or you can do it together with other stuff, or you can, whatever, right? And so moving to how this is most typically put together in data engineering is a medallion architecture, or something that looks like it, right? This is like some good branding stuff someone came up with that for something that's been done since time immemorial, which is first, I'm gonna land my data. I'm not gonna touch it, I'm just gonna move it and put it somewhere in my lake, my warehouse, whatever it may be. Then I'm going to clean it up a little, right? I'm gonna not necessarily apply a ton of business logic, but maybe some business logic, not exactly sure how much, but whatever my architect tells me, right? Or tries to govern, I'm gonna do that next. And then finally, I'm gonna put it in the gold layer, right? Whatever that may be, which is, business level aggregations, et cetera, right? And so we talk about separation of concerns, right? And, segmented, what changes where. This is a instance of that, right? It's very general, right? Every company kind of does this one a little bit different. You end up oftentimes with like 600 to 600 layers right around here. Again, it is interesting because they spend a lot of time focused on the storage. That's the thing that people can grasp the most. But in reality, the thing that matters way more than the storage is your code. And there's zero definition in any of this stuff about how to structure your code and what are the actual steps and stages and defined elements of the processing steps that are all around these layers. And so that is a con. I mean, it's just tough. There's a lot of work to be done here in order to help bring the separation of responsibility and the single responsibility principle into the data engineering space. Cool. All right, we're two for three. Lastly, pure functions only. So data pipelines are imperative. Imperative means you declare them, we do this first, then we do the second, then we do this third. By definition, it's called a pipeline because you're going to move from left to right? You're thinking of this thing first, you're going to store some data, and it's all about step by step. And then the other very important piece of this concept is the state. So in computer science, state is something everyone thinks about. In the data world, we don't really think about it because everything is state. Because data, we're working with data. Data is a stateful thing by definition. So essentially, the way that this works versus a functional is with functional programming, you're thinking more about the logic and the results. And applying it to the data, we'll get on the next slide, you see how this kind of applies to data world and how we should be thinking about functional programming in the data world. But our goal with pure functions, whether it's software engineering or data, is we want to have zero side effects, meaning what we are building in our function, we're saying, A plus B plus C equals D. We want D to be as narrowly scoped as possible, and we want it to not actually have a secret C, secret X, right? That it's actually modifying off to the side just because for fun, right? It's no, it's only touching D. It's only going to change that state. It's only going to modify that one element that it says it's going to modify. There's nothing else happening just because it's convenient along the way. Ultimate composability, again, if you do this really well, you can basically reuse these in a much more fluid way. You don't necessarily need to worry about what kind of order they're composed in or how they different thing, right? If the inputs are available to you, you can plug them in because the function itself has nothing to do with the context of the inputs or the context of the outputs. It just does what it does, okay? And then finally, dry by default. If you do this really well, right, you don't end up with that code duplication because you're able to reuse everything in very small bits. There's no reason to rewrite your code. You just basically point to the previous function, right, versus having to copy paste that logic of that function somewhere else. Okay, we've gotten pretty advanced, we've gotten pretty deep. Everyone more or less following? Again, we're like lots of theory, time for some fun. This is what pure functions look like in data engineering. Again, we talked about scope of targets, right? Pure functions, really simple. You got some stuff in, and you're going to then write, ideally, to basically one cell. Now, this isn't like exactly how it works, right? We work in sets. So it's really like, hey, we have X number of rows on the inside, or X number of columns on the inside, but ultimately we're creating one result, right? Almost like a scalar result, right? If you think about like an Excel formula or something, for every set of inputs, we're generating one cell of output. That's the best. That allows us to do basically anything, whatever we want, in all the best ways. Scalar calculations, if you're familiar with that language, that's what they're great for. UDFs, by definition, are the same way. And then my favorite that is a little bit unintuitive is roll-ups to current grain, right? So say you have your table that exists today, it's your, we'll call it the header table, right? If you want to take all of the transactions under that header, the line items, for example, and you want to roll them up to the header grain, you can write a function that actually works over many multiple rows of other tables. But the result of it, right, whether it's a sum or a product or a first or a rank, right, that is going to then just ultimately result in one single result at the grain that you're working at that header grain. So again, there's very powerful. If you really focus on this as a core tenet, you can do a lot of stuff in this first group of functions. Second one, semi-pure. Basically now your context of your target is a single column, right? But you can touch other rows, right? So the best ones like window function, ranking, classic stuff, right? Hey, I need to take all these columns, all this stuff, and I want to then rank them, right? 1, 2, 3, 4, 5. And hey, I got a new data element that comes in. It's going to necessarily, if it's suddenly that new data element actually is ranked 2, it's going to then push down the resulting data set, the data elements for 3, 4, 5, right? The old 2 is now going to be 3, the old 3 is now going to be 4, the old 4 is going to be 5. So you're technically modifying potentially every single row in the column, but that's kind of what you need to think of, right? What's this potential scope of the function that I'm writing and what's the potential output? And then last but not least, it's the everything else, right? Sometimes it's just really convenient or really concise in your code or really straightforward to just write stuff that just modifies everything because you just need to, right? Again, classic thing is change data capture, refresh processes. When you're actually thinking about like tracking and persisting refreshes, you're changing all the columns, right? Everything could change at any time because the incoming data could have, any of the columns of the incoming data could have changed at that point. Another good one is unpivot, right? Unpivot's a classic one where the number of columns that it generates are the number of distinct values in the rows. And so you have no control over that. You have no idea what's even going to come out of it, down the road. So hopefully, right, there's some governance in the source system, but programmatically, you never know how many columns you're going to get produced with that type of function. Okay, so this is kind of the most important final piece that kind of combines everything together because the dream is to write more functional code. We'll talk about how we do that next. Anything else? Questions now? Is everyone roughly following along here? Like I said, we've gone deep. We've come up for air a little bit. Quick review. We're now dry. We now know why things should be in separate places. It's better, helps you organize your code, helps you govern your code. And lastly, pure functions only. We really didn't talk about what all the awesome benefits are yet, but we did talk about what it is, right? And how it applies to data engineering so that you can start thinking about your logic and start thinking about what you're writing in the context of what is this changing? What and how is this changing? And how can I make it so that they can move more towards the top if I have the choice? There's many different ways, right? Very flexible with different ways to write relational algebra in SQL or in pipelines or in logic. The more you can put that looks like the top stuff, the more composable, the better, more reusable your code will be down the road. Cool. All right. Now we get to talk about the way that we did this with DataForge. This is generic. This is the way we did it at DataForge. You could do this yourself, but I'll just say, right, we are now going to talk about the product a little bit, so apologies. We're going to break down SQL into its component parts, and hey, here's the select portion, here's the where clause, here's the join, and in fact, especially the select portion, we're going to look at the functions of the select portion and say, all right, which one of these are pure, which one of these are impure, which one of them are not, right? We're going to break it down, then we're going to do something with it. Next is build a system to check for dryness. Again, we talked about my favorite statement, right? Everything's got one place to live, and it's the authoritative place for it to live. Well, that's great. Let's go actually put it somewhere. In this case, we're going to put it in the database, and that database is going to have checks in place to make sure there's only one copy of it. So that even as a developer, you're going and you're like, hey, I want to add this thing. Well, Joe from 3 years ago may have also added the exact same thing. And without having to go and look through his code, every single line of code to see if someone wrote the exact same thing with you, we should have a system in place to check, to say, oh yeah, hey, Joe actually wrote this 3 years ago, just use that function. Don't rewrite it again, just go use that one. Oh hey, great, this is great, I don't need to write this now, I can just use that one. Next up, we need to take all of these things we've broken down, right, into all these little parts, and we need to make them into something usable. right? So these parts are not usable, they're not executable in any runtime because they're just all these arbitrary parts that we broke down. We need to find a way to then bring them all back together into then something that's useful to execute, useful to run, actually does the transformations and takes your data sets and moves them forward. And then finally, this is, I'll call it a bonus step. You don't necessarily need to do this, but we thought it was very valuable, which is to then reapply SRP to basically take the medallion architecture and take it a whole step further. And do it with all the processing steps, do it with all the storage layers, admit that it's not gonna all be done in 3 easy steps, and take an approach to say, all right, well, how few steps can it be done in, and define that, and then plug that all in with everything we put above into one easy to use data flow, storage layer, code language. All right. So this is how we broke things down. Data Forge says non-comprehensive. We'll get to the next page where you get to see more comprehensive view. But this gives you an example of the process we went through, right? You look at all the different things you end up doing in SQL, and you look at them as, what am I doing with it, right? You put a name to it, easiest one's aliasing, right? I got this column, we're gonna call it this column. You're not actually doing anything, you're just renaming it for maybe business purposes, or maybe the source system's got some ridiculous, terrible naming scheme like SAP or something. You need to put some actual language in there so that it can be human readable or workable. Scalar calculation, we talked about those as pure, right? Basic addition, multiplication, straightforward stuff. Again, more advanced than we do. Aggregation, break down into 2 places. Even though you're thinking, oh, aggregation is just one thing, let's start there. Once you dig in a little bit further, you realize there's a couple different types of aggregation that happen. First one is, I already have the grain, right? I'm essentially doing a roll-up. We talked about that example with the header and the line detail. That's one type of aggregation. And then we've got aggregations where we're rolling up to something that doesn't exist yet, right? We need to create a new grain of data based off of some combination of dimensions or some combination of data elements, and that's different, right? That has a different scope of functionality, or functional, completeness. Where I'm working on the whole table, right? I'm changing the grain, I'm changing the rows, right? Whereas the aggregation, I'm not. It's more straightforward. Filter, same idea, right? I'm changing the number of rows. So that one, again, kind of looks like the new grain, if you think about it, right? And then, of course, we've got joins. And there's a million different types of joins and a million different ways to work with it. Like I said, non-comprehensive view. But let's pick the most straightforward one, left join, right? We're gonna do a left join, we're gonna take our existing data set, we're gonna add on some stuff, and then we're gonna do a lookup, do a join, and tack those on. But what we're gonna do is we're going to take that and take that bit of logic that says, hey, this table is connected to this table, we're gonna put it somewhere else. It's not gonna be in a SQL statement, it's not gonna be in your script, it's gonna be in its own object, in its own separate place, so that again, you got one place for your joins to live. Just like building a data model in Power BI, for example, right? In the Power BI data model, you only write your connections between your tables one way. Why wouldn't we do that in the data engineering space, but with code, rather than drag and drop and all this other stuff? So in this case, we're taking joins, put them in their own special bucket, own special object. So as you can see, right, we took things that look similar. Going back to SRP, it's not about what they do, it's about how they change. So again, aliasing, scalar calculation, aggregations, these all things change the data and the input parameters for them, all change in the same way. So we said, all right, these are all basically a rule. We're gonna call that a rule, we're gonna make up a new name, we're gonna call it an object, and we're gonna store it in a database. Same thing with the channel mapping. Aggregation on a new grain or a filter, right? Essentially what you're doing is taking and creating a new grain of data, right? Whether you're filtering, just taking a couple rows out, or you're rolling it up. That's a new grain of data that wasn't there before, that wasn't consistent with queues or otherwise refresh processes. And then lastly, I think about joins, they go to their own thing. So again, non-comprehensive. This is a more comprehensive view, but I didn't list out all the different transformations. This is a simplified meta model. So what we did is we took all these objects, and we're database people, so what do? We put them in a database. And we modeled them all together, and we build relationships between them. So now we have a meta model, all of these objects that we broke down SQL, we thought about everything you ever do in terms of transforming your data, we broke them down into bits and bytes, and then we put them into a database. So again, 2 parts. You put it in a database, and then you build services to make sure that there's non-duplication, that there's referential integrity, that, hey, I took a SQL statement and I broke it down, this thing needs to point to this thing, it needs to point to this thing in order for it to then actually be composable and able to be turned back into SQL on the other side. A million more checks in here, we're not gonna spend a ton of time on it, but hopefully this tracks, right? We've taken the SQL statement, we've thought through what are the different ways by applying these software engineering principles, bring it together, store it somewhere. So now we have all these things broken down. It's like, okay, great, we've gone through this whole process. Why do I care? What does it matter? So how this end up working is you then need to, again, take it from the broken down model. And as a user now, I'm not writing SQL. I'm writing just the individual elements of SQL, one object at a time. So now my scope of development is no longer the entire set or the entire pipeline or the entire everything I need to worry about, and you have the context of everything else that's happening in the system. My focus now as a developer is what is the function I need to write in order to take these couple columns and create a new column to do the type of business transformation that I need to do. So again, you're able to then take this giant world of everything that's in the system and narrow it down to just one single business department, one single transformation you need to do, and focus on that as a developer. And then the system is here to help you do a whole bunch of checks, right? Hey, has this been written before? Hey, does this point to something that actually exists? Hey, is the downstream stuff from this gonna blow up on me because I ended up doing something that's gonna change the scope of my function? These are all things that you're then able to just work with at a much more simplified level. And then you need a SQL code generator because this is not runnable. It's just configurations, right? This is just a bunch of small code snippets that are useless by themselves. It's not SQL, it's snippets of SQL. So then you gotta put through a code generator to then do stuff, right? Okay, well I wrote some code and as part of that code there's a new column. So I gotta write some DDL that generates an alter statement to take my intermediary table that I was gonna write the code to, and I need to write an alter statement to add that new column, and then I need to take the function that referenced that and create it. So on and so forth with kind of the pure SQL and impure SQL. Pure SQL, we can do all at once. The coolest part about writing functional SQL code is it is composable and intercomposable, meaning there's no need to do intermediary storage layers. If you have all pure SQL and all pure functions, there's no reason not to do it all in one shot. One of the most expensive thing you can do in data engineering is writing data to disk. So the less you can write data to disk and the more stuff you can keep into memory. And again, all the distributed computing systems are really good at this. Pruning memory and taking things in and out of memory, as they need to, as the processing chain continues to move forward. You're able to basically do this kind of all in one shot. Impure SQL, by definition, you can't. So we gotta break that out into whole separate query gen to then put everything else, right? So it's like we gotta change the tables ahead of time. We then gotta run everything. And again, the more stuff you can fit into here, the better. And then it's the everything else, right? As the, okay, now we actually need to take the next step and separate that and potentially do multiple steps, right? In order to finish writing all that rest of the SQL. Okay. We're doing a lot. And then of course, it's like, we've written all the SQL now we need to orchestrate it, right? So we have SQL, great. What do you do with SQL? You gotta figure out what order to run it.
So is it only for preventing and building, or can you use it to clean too?
I'd say cleaning up code. The way this works is we're working with partners who are building mapping processes from existing scripts. So if you want to learn more about that, I'm happy to give you details. But essentially, if you ask those vendors about who do code migrations from, Teradata to Snowflake or Teradata to whatever, or Snowflake to Databricks or whatever, what they're actually doing under the hood is almost identical. They're actually taking all of your Python code, your tables, your schemas, your queries, and they're breaking it down into their individual elements. Usually it's just a big bunch of JSON that they break down into, and then they have a mapping process to take it from source data to their JSON storage, and then to their target system. And so they basically are then just building adapters from the source systems or adapters to the target systems with their nice JSON format in it. So for us, they really like us because they don't need to generate a whole bunch of code after they put in their JSON. They're just basically just mapping it into our own structure that powers the rest of the platform. So that's how you kind of get over into this place quickly, but bluntly, building it from scratch is also really quick and easy. And I'll take one more step back and say, this is all great, but remember this talk is called Building Extensible Data Code. And the whole reason we end up going through all this trouble and doing all this crazy crap and unwinding SQL just to wind it up again is so that when you make changes, you don't need to think about everything in the whole system And if the best place should live over here, the best place should live over here, you just take your business logic and you apply it and you're done. We'll talk about orchestration in a second, but that is the goal, right? I should have a system in place that can just take the little bit, I can add it on, and then I'm done. And it's there, and the system's there to check for, again, duplication, reuse, all these components of best practices. Okay, so we talked about how we took the medallion architecture and we blew it up in a good way. So now we're gonna take the SRP, single responsibility principle, we're gonna apply it to the processing chain. So rather than, again, anything everywhere all at once, no. Everything in the exact same order every time. And so we're gonna ingest the data, we're gonna optionally parse it. Some of these are optional steps that, if you don't need to do it, you don't do it. But we're gonna tell the system that we don't have to do it. Then we're gonna do capture data changes. This process looks at everything that's ever been in the hub table before and flags every single record with new, changed, old, unchanged, whatever. We're then gonna take just the change stuff, just stuff we know we need to move forward from that process, and we're gonna apply our pure functions. And so we're taking all the stuff that we know is a scalar operation that doesn't need to touch every single record that's ever been loaded before. We only could work with just this batch of data, just this set of change data that's coming in, and that is much more performant, right? The least amount of data you can possibly do your transformations on, the better. And that is also can all be done in one shot. So we apply all that logic as part of the enrich step, and then finally we call it refresh recalc. We do it all in one shot, where we take the results of change data capture process and enrich, and we do all the calculations that hit those multiple rows, right? So window functions, sometimes self-referencing lookups, sometimes lookups that go to other tables that need to potentially change like a master data lookup, right? If a reference value changes, you potentially need to add and change every single row in this calculation, so on and so forth. And then finally output, this is where the magic happens, where you can take a subset of every function or every intermediary step of each function and just point an output to that step or any intermediary step. So this is the thing that's kind of hard for me to show visually. Again, I would be happy to talk you through it, but this is the really most important part. If we do everything purely functionally, right, we end up with this chain of functions, and really what it ends up being a tree, right, like a map, a tree of functions that you've built as you're developing and adding one at a time. This one is derived from this one, is derived from this one. What you can do, if you set it up right, if you persist the result from every function, that allows you to then on the output side, just grab the results from any function, any chain of functions, any intermediary step. So therefore, you have a two-step process. I write my logic, I build my logic, the system helps me understand whether it's pure or semi-pure, I do all those calculations, and then finally output is where we do our aliasing, because why do mapping and aliasing before then? Only one place for it to live. And we point to the upstream logic we wrote to say, I want to grab this function result, this function result, this function result, and persist them in a target. Okay. And then finally, right, goes for a target. And then finally, any good data engineer knows that it's never that simple. You always then need to do something extra, or I need to write some custom stuff after the fact. And this custom post output is there for you to basically work completely outside of everything we just talked about and just write some darn SQL or some Python or some Java or some Scala or whatever you need to do. So, and then finally, the last thing I'll say is, you're like, well, hey, look, even in my best possible scenario, not everything can be done in one shot, right? There are just situations where it's just not possible. So, very simply, what happens whenever you get through this whole thing and you know you need to do something else? First, you challenge yourself. You say, can I fit it upstream? Is there any possible logical way for me to fit it upstream? The answer is no. Okay, cool. We're going to take this output here, and we're going to do a loopback is what we call it, and we're going to use that, and we're going to ingest it. We're going to take the result, and we're going to pass it through the whole pipeline a second time. But there's no decision making on what these steps are within the scope of this flow. As an engineer, everything goes through everything, and if it doesn't work and you need to add another layer, you start a new independent pipeline that has the exact same steps as this. Okay. We've now gone into the dark zone of all kinds of complex stuff happening. The long story short is all of these software engineering principles, we just touched on 3. There's about 6 others if you want to, come hang out with me and nerd out for a couple hours. are all ways that focus on writing extensible and dry code, right? The less the less duplication we have in our code, the better. The easier that we're able to add stuff to our platform, the better. Because our ultimate goal is to get away from the chaos, right? And so if we can do that, we're winning. SRP and pure functions are a solution. There's many other solutions. Some of the other vendors here are giving great talks on other ways to solve this problem and other ways to apply best practices and software engineering practices to the data engineering space is a big trend. And then, again, 3, 4, 5 is really how we did it, is the way to break things down and then roll it back up. And that's really the difference between the way we approach things versus a lot of other orchestrations are doing and other things. And I'll say is the coolest part about what we have and the combination of that whole functional craziness we went through and the standard processing flow is you don't do orchestration. You just don't do it. Everyone's like, we're gonna have an entire product around building orchestration. You don't do it. You write functions, functions point to other functions, and you have a standard pipeline that always executes the exact same way every time. And so now as an engineer, there's no orchestration. The system understands what functions need to run in order for the pipeline to execute successfully, and it can then dynamically build SQL statements based off of where the data is, when's the last time you refreshed it, did you add a rule since the last time you refreshed it, what are all the different bits of metadata floating around that we track and then allow you to basically just hit the go button at any point of any flow, and the system is basically then responsible for making sure your data integrity is correct for that output that you've defined. So that's like the ultimate win is as few and as simple steps you can do, better. I think we're over time? No? So, we're good.
We're just taking pictures.
Oh, pictures, oh good, cool. I can say we should have like 15 minutes. Yeah, cool.
I'm trying to be as disruptive as possible.
No, it's good. No, I don't know.
Super disruptive. On the roadmap, yeah.
But again, rolling it back in conclusion, right? Our goal is to avoid the spaghetti code. So even though this is like complicated as heck, and there's a million things to learn, and there's all these different concepts, this isn't really about building it the first time, right? Building it the first time, bluntly, pipelines are pretty straightforward, right? Put the stuff together, build it, get the results set, it's great. Doesn't matter what language you build it in, doesn't matter what technology you're using, pipelines are a great way to build the first thing. The challenge is then adding to it. You have 1,000 pipelines, you have one new column you need to add. Where does that column come from? How many different packages are the lineage from it? What do you need to change? What do you need to refactor? What do you need to regression test? Because you had to go change 20 packages, and even though just to add that one column, I now need to go retest not only those 20 packages, but every single data element that those 20 packages touch. And so next thing you know, your boss says, hey, I just want this new column for my report. And you're like, oh crap, that's like 2 months of work, right? Because you need to not only go back and learn all the things that the 3 developers who aren't you, who were there 6 years ago, developed, but you need to then go in and potentially understand the impact analysis of the changes you need to make and how it may blow up production and cause chaos. So if we can avoid that by going through, again, something that looks like this, then we got into a better place that makes it more extensible, easier, faster, for you to deliver value and for you to get to the end goal better, faster, stronger. Yeah, and again, classic pitch. Come check us out. We have a solution to a lot of this stuff. It's just an approach. We're pretty passionate about spreading the word on taking this type of logical approach to solving this problem. We're very open about our entire meta structure. We're very open about all the details. There's no secrets here. There's just a lot of moving parts for that whole system to do all those checks as you're developing code, and that's really what our product does. All right, thanks very much. Questions?
Can the data force solution be applied to an existing pipeline?
It interoperates with existing pipelines. So
Because,
going,
as you said, right, the complexity only arises when you're trying to maintain a big pipeline. That's
Yep.
when I think people would need the solution like that.
yeah, so for example, in here, right, a scalar function is a lookup. So we have something called a unmanaged source in our platform, which means that, hey, you have a separate set of pipelines using a separate set of tools. Maybe you got some DBT stuff going, maybe you got some, Airflow and some other technologies or just scripts, stored procedures, right, that are out there and they persist to a certain table. you can reference those tables because under the hood, we're just Databricks. And so if you got it in Databricks somewhere, or in some, Databricks now is federation into like everything. So if you can, have a federated connection into even a, maybe sit in Postgres somewhere, you can then reference that as a lookup column as just part of your functional programming that you have in our technology. So we interoperate with everything. We work with third parties natively because again, we lean in on Databricks really hard for all that stuff, right? We're the code management, code orchestration, all that good stuff, but under the hood it's just vanilla. There's nothing, no magical processing system, it's just running Spark, and it's just sitting in, depending on details, either in Parquet, Delta Lake, or otherwise. What else you guys got? It's good. I feel pretty good, because that's like, I got like 40% glazed eyes. And, that's pretty good. It's my first time going through this, and it's definitely a lot to kind of plow through in a short time. And yeah, that's definitely one of our challenges, is to, you guys are the right audience, to try to give this speech to. So appreciate your time and attention today.
What's the actual developer experience look like? When you talked about kind of
Yeah.
what you gain from it, but not necessarily what it looks like to do the thing.
Yeah, so I'll come over, I'll give you a demo, but I'll just say there are two ways to work in our platform. First is we have a UI, and that UI is essentially a structured approach to coding. We have a whole bunch of checks, think of like an ID, right? Your developer environment, it's got autocomplete, it's got all these different elements where there's specific places in our UI with specific text boxes where then it's like, all right, I'm gonna enter this object's configuration or this object's code or this SQL expression for this bit and byte. You can go through that whole process, we recommend it. There's a whole bunch of checks in place. It checks your syntax real time so that it doesn't even let you save bad code. It doesn't like do it the database side, it doesn't even let you enter it. It'll give you real-time feedback. Hey, this is gonna error out for this compiler later on, and so on and so forth. The second one is we have a YAML-based configuration language. So if you just want to code, you can go ahead and code your butt off. And that YAML configuration language, you're configuring the objects, right? You're configuring the individual elements of the single rule, the single channel mapping, the single elements, right, of that meta model in the YAML configuration language. And then after you've done that, today, you then shove it into our import process and it compiles it, gives you feedback, says, hey, this reference isn't right, you're not pointing to the right thing the right way, this error is you're not doing an aggregation correctly because it's gonna blow out the grain and, you got a million records on this side, a million on this side, you got a million and one on the result set. Our system checks for that type of stuff to make sure you're not gonna cause that type of chaos. And then you get feedback, you go through and then try again, right? Fix your YAML, go through it. On our roadmap is a CLI, right? Where if you don't even want to talk to our UI, you just want to just be a developer and just really develop with your text boxes. We're adding a CLI layer on that will allow you to just compile locally and do all that stuff if you want to. Cool. Yep. What else? Anything? Hi, Paula.
Is it possible that they can see the platform today upstairs?
Yes. Come check by our booth. We have an interactive demo. It's like a non-live environment that you can click through. And then, of course, we've got the product. It's a web-based GUI. And for those of you in the healthcare space, we have both a SaaS version and a private cloud version. So you can use our stuff, not worry about the infrastructure, not worry about our back-end services, our databases in Postgres. Yeah. One of the last cool things that I like to highlight about this product too is I mentioned that under the hood of all these objects is a database. So actually all of your code is data. It's in a database. So you no longer have to think about observability and meta repositories that are scanning code and then trying to figure out the lineage of everything. You're actually building the lineage and building the observability metadata by configuring the platform. And then our services are responsible for scanning all of that lineage, all that metadata, all that stuff, and generating all the SQL that then needs to run to make that possible. So it's like taking the whole paradigm and flipping it on its head, right? You as a developer are building metadata, not building code, and then really hoping that your observability tool figures it out just perfect after the fact. And it's great because you can query it. Like, hey, how many things are using this type of function? Oh, great, you just write a SQL statement. You got it. Okay, that's it. I'll let you guys go. Thanks so much for the attention. Have a great day.